Oh, hey, 8th graders. Today's lesson is 3.2 phase change. And your learning targets today, I can compare and contrast the molecular attractions of different substances, and I can explain why two similar substances are different phases at the same temperature. So if you guys think back to last week and lesson 2.2, we had a little video that we watched that talked about oil and butter. Okay, at the same temperature, they are two different phases, but really they're very similar. They're both fats, they're both oils, however you guys want to look at it. So why are they two different phases? And that's what today's lesson is going to kind of focus in on, is what's the difference between the molecules in oil and the molecules in butter, that even though they have the same average kinetic energy or the same temperature, they behave differently and they act as either a solid or a liquid. So that's, again, what we're focusing in on today. So first activity for you today is your notebook. So open up your OneNote and add molecular attraction to your vocab. So molecular attraction is a pull between two molecules that is always the same for a substance. So one of my favorite examples to give for this is water. Okay, you guys will notice that water doesn't always behave the same as most liquids. So for instance, you guys can take a dropper and drop water onto a head of a penny until you guys kind of get this bubble shape that forms on a penny. So molecules in water have a different attraction for each other than other liquids do, say rubbing alcohol. You guys couldn't do the same thing with rubbing alcohol. Water skippers are another example. If you guys see the little insects that float along the top of the surface of water, their feet don't actually dip into the water. They're able just to stay and kind of walk on top of the water. Again, if you were to put a water skipper on some other liquid that isn't water, it wouldn't be able to stay on top like it does other substances. So that all has to do with this concept of molecular attraction, which is, again, really what we're focusing on today. Okay, and then you guys are going to add key concepts 9, 10, 11, and 12, and 13. Okay, so you guys have a couple key concepts to add to your page today. So whether or not a phase change occurs is determined by the interaction between the kinetic energy of the molecules and the attraction pulling the molecules together. So again, it's going to be this concept that kind of frames out why oil is a liquid at room temperature versus a stick of butter is a solid at room temperature. The molecular attraction of a substance never changes, so it doesn't matter what you do to that substance. As long as it's still that substance, you could heat it up, you could cool it down, whatever the case, as long as it remains that substance, it has the same attraction between molecules. Okay, 11, 12, and 13, a phase change occurs when the kinetic energy increases enough to overcome the attractions between molecules. It's kind of the same kind of concept of thinking about a magnet. Okay, you can pull a magnet apart, but only if you have enough energy to do so. So if it's a really strong magnet, you need more energy to pull that magnet apart. If it's a really weak magnet, you don't need enough as much energy to pull it apart. 12, a phase change occurs when the kinetic energy decreases enough so that the attraction between molecules pulls them together. That's really the opposite of what we just read in 10. And then finally, different substances can either have weaker or stronger molecular attraction, and that's going to be really the key to all of this, is that because we have different substances and their molecules behave differently, that's where this attraction is coming from. All right, so here's your warm-up for today. Imagine a drop of rubbing alcohol and a drop of water are dropped on your desk at the same time. So we have rubbing alcohol versus water. Okay, the rubbing alcohol will evaporate. You guys are going to use the draw tool to circle your answer, either at the same time as water, faster than the water, or slower than the water. And then explain your answer. Why did you choose the option here that you chose? All right, moving on. So in class, we're actually doing this experiment, but if you guys are DLI or you were absent, you guys will watch this really short time-lapse video that I made that demonstrates the exact same thing that you're going to see that the kids in class are doing in class. Okay, so watch it. It's about 18 seconds long. I filmed it for about 5 minutes, but again, it was time-lapse, so you guys don't have to sit and watch water evaporate for 5 minutes. So go ahead, check out what the instructions look like. You guys see it happen in like super speedy motion, and then see what your actual results are. So did the water evaporate after 5 minutes? Circle yes or no. And does that fit with your prediction from the warm-up? So that kind of goes back to here. And then did the rubbing alcohol evaporate after 5 minutes? Yes or no. And does that fit with your prediction from the warm-up? Okay. All right, moving on to activity 4. You guys are going to watch this little video here. So right click and open your link. It looks a little something like this. So we did this demonstration in class, and again, those of you guys who are DLI or doing this from home, you guys also saw this same demonstration with these colored magnetic marbles. Remember, each of the marbles represents a molecule. So in this box, you guys will see just the regular marbles you saw the other day, and in this one you have some stronger magnetic marbles, so they have a lot stronger attraction. So you guys can kind of see how adding energy to each of those boxes of marbles is affected by how strong those marbles stick to each other. Okay, so how they move is based on how those magnets are attracted to each other, which again is that same concept. If we look at one of those marbles being a molecule, molecules have attractions to each other as well, and some are stronger than the other. Okay, all right, moving on from that, once you guys watch that, you're going to move on to activity 5, which is a little reading. It talks about making liquid oxygen. So you guys maybe have heard of liquid nitrogen, maybe you've had dipping dots before where you or seen how dipping dots are made. For those of you guys who don't know, dipping dots are ice cream that are sprayed over a giant vat of liquid nitrogen, and the second those little droplets of ice cream solution hit that liquid nitrogen, they freeze into the little dipping dots and they kind of precipitate to the bottom, and then they're filtered out and you're fed those. It doesn't hurt you because the liquid nitrogen disappears shortly after the ice cream comes into contact with them, and what you're left with is just fun little balls of ice cream. Okay, in this case you guys are going to learn about liquid oxygen. Okay, so liquid oxygen is made in a lot different way than liquid nitrogen. But you guys will also see liquid nitrogen tied in here. And then again, you guys have heard too of solid carbon dioxide, which we know is dry ice. Okay, so main thing I want to kind of describe with you guys is it talks a little bit about attraction of molecules here, but then it gets down into the nitty gritty of how liquid oxygen is made. And I just wanted to kind of go over one figure for you guys to show you guys really quick. So right here it says when scientists need liquid oxygen, they can get it by separating just basically the air around you. Right out of the air. So air is a mixture of nitrogen and oxygen, so most of the air is nitrogen and oxygen that you're breathing in, combined with small amounts of other gases like water vapor and carbon dioxide. Since the gases in air have different levels of molecular attraction, scientists can separate them by sending the air through a machine with different tanks that are at different temperatures. So you guys can see this little diagram here. It shows you tank 1, tank 2, tank 3. So it takes in regular old air, so air containing mostly nitrogen, oxygen, water vapor, and then some carbon dioxide enters this machine. And in tank 1, the tank is cooled and water is drained away. So when they cool this, they don't cool it a lot, but they cool it enough for all that water vapor in the air to turn into water, and then that water is drained away. And what's left is this gaseous nitrogen and gaseous oxygen still without any water vapor in it. Okay, then that nitrogen and oxygen gas are moved into tank 2. The tank is cooled even more, producing a mixture of liquid nitrogen and oxygen. So now it gets rid of any other gases in this process and leaves us with liquid nitrogen and liquid oxygen. So we have a really, really cold tank right here. And then that liquid nitrogen and oxygen mixture is pushed into tank 3, and it's slightly warmed up a little, and this is what separates the nitrogen from the oxygen. So when we warm it up just a little bit, okay, that liquid oxygen stays as a liquid, but we warmed it up too much for the liquid nitrogen to stay a liquid, so it turns into a gas. That that gaseous nitrogen is removed, and we're left with liquid oxygen, which is this really cool blue fluid that you guys see right here. So it kind of has a pale blue appearance to it. So I just wanted to walk you guys through that procedure. You guys will read all about it, but it's kind of a cool procedure as to how they make that. Okay, so once you guys read that, I want you to answer this question. Why does an energy transfer not always result in a phase change? So if we look back at that diagram, for instance, right here, we have a energy transfer here that turns the nitrogen gas into a gas, but leaves the liquid oxygen as a liquid. So right here, they were both liquids, and a slight energy transfer changed the nitrogen into a gas, but left the liquid oxygen as a liquid. Okay, so why did that energy transfer not turn our liquid oxygen back into a gas? I'll give you a hint. It has something to do with the attraction of molecules. So really think about this, okay? Which has a higher attraction in their molecules? When those two are heated up, the nitrogen moved away from each other a little bit quicker than the oxygen did. So which one has molecules that are attracted to each other more? Again, Think about that concept of the magnetic marbles. Okay, if we add a little bit of energy, one of those have all the marbles separate versus the other one has all the marbles stay together. Okay, so think about attraction of molecules, and then again, use that marble, those magnetic marbles as a good example for you. All right, moving on, we're winding down with our lesson. Last little part is a simulation here. So launch the sim, here's your link. Then follow the instructions below to test the investigative question. How does molecular attraction affect whether or not a phase change will occur? So as you complete the activity, answer the questions provided. So first test you're going to complete is you guys are going to look at substances B and C. The first partner should test substance B while the second tests substance C. Obviously, if you're working from home, you guys are testing both of those. When you are finished, compare your results. Note, substance B has a medium molecular attraction while substance C has a low molecular attraction. So if we hit play and look at this in our sim, we have B right here is medium and C is low. Okay, so before you guys go on to test this, I want you guys to make a prediction. So before starting, make a prediction. If substances B and C are both in gas phase and are at the same energy level or the same temperature, which of the two substances will need to have more energy transferred out in order to change to the liquid phase? Substance B or substance C? So again, you're transferring energy out. You're going to try to cool them down and turn those gases into liquids. Okay, then go ahead, transfer in energy to reach the highest amount of kinetic energy for B and C, and then slowly transfer energy out of each substance. Note the temperature at which each substance changes phase. So you guys will need to tell me, when did B turn to a liquid and when did C turn to a liquid? So at what temperature in degrees Celsius? And then finally, based on your observations above, which substance needed a greater decrease, so we had to change it or transfer energy out the most in order to change phase. So you guys use your draw tool to circle either low or medium. The substance with blank attraction needed more energy transferred out in order to change phase. So again, look back and review which substance out of B and C was low and which was medium. Okay? You guys are going to do something similar in that, except we're looking at substances A and B. And again, in this case, we're going to be trying to change their phase differently. So the first partner should test substance A, while the second tests substance B. Again, if you're at home, you're doing both of these. And when you are finished, compare your results. Note, substance A has a high molecular attraction, while substance B has a medium. So this is kind of flipped. You guys get to see what that high molecular attraction looks like. So make a prediction before you start. If substance A and B are both in the solid phase and are at the same energy level, which of the two substances will need to have more energy transferred in order to change to a liquid? So we're going from a solid to a liquid, so melting. Substance A or substance B. So here's your directions. Transfer out energy to reach the lowest amount, so we're turning them both to a solid. And then slowly transfer in energy to each substance. Note the temperature at which each substance changes phase. So again, we're looking at melting here. Substance A changed at what degree Celsius, and what did substance B change to a liquid at? Okay, and then based on your observations above, which substance needed a greater increase in kinetic energy? So which one did we have to crank the most energy into to get it to change phase? Was it the high or the medium? So the substance with blank attraction needed more energy transferred in order to change phase. All right, last little question on the sim. Two substances, both solids, start at the same temperature. You transfer the same amount of energy into both solids, but substance 1 becomes a liquid before substance 2. Based on this evidence, which substance has a stronger molecular attraction? So use your draw tool to circle either substance 1 or substance 2 and explain your answer. All right, final part, you guys have 2 questions to answer. What do the images below tell you about the molecular attraction of substance A? So you guys can see substance A at 36 degrees and substance A at 206 degrees. So this one's significantly hotter. Looks like both of them are still acting like a solid. You guys can tell the difference in their kinetic energy, but what does that tell you about the attraction of A? Next one, you guys are going to compare. This again is the same thing I just went over, and this is the reason I went over that in your guys' article. Okay, in tank 3, we noticed that we heated up our tank just a little bit, and that had a phase change for our nitrogen. It removed it from the liquid phase and into the gaseous phase, and then we were able to filter the gaseous nitrogen out and leaving us only the liquid oxygen. So the liquid mixture is then moved into a third tank that is heated up just a little bit so the nitrogen evaporates. The kinetic energy of the nitrogen becomes too strong for the attraction between molecules, and they escape into a gas. When the nitrogen evaporates, the liquid left behind is mostly oxygen. So what do the images below tell you about the molecular attraction of oxygen molecules compared to nitrogen? So again, same thing that I just had you guys think about answering that question after the article. So which of those has the higher attraction? Is it the oxygen or is it nitrogen? Again, think about those magnetic marbles and how they relate to that. Okay, finally, complete your wrap up. Do you have any questions? Circle yes or no. If you have questions, type them below. And then finally, 4, 3, 2, 1, how do you think you did? Obviously, if you have questions that are preventing you from finishing this, go ahead and send me a message in Teams and I can help you out. You guys are all done. Don't forget to hand it in, and I hope you guys are all having a splendid day.